So,
Alright, so our final project is building a sports strike classifier. The motivation for this is not what was written there. The motivation for this is the fact that this guy does a very good job of fencing. And me and Ben just wanted to hold a sport for the first time. And here we are.
So the system overview. The way we does this is that we use the onboard IMU to record accelerometer and gyroscope data, and then after we have that, we pre-process it using spectral features, pass it through a DNA, and then flash it onto Edge Impulse, and we build a external web interface to do live classification. And we're gonna demo that in a second.
So the way we collected data for training is we basically, like we said, collect IMU data from the Arduino, and then we send that over Bluetooth to a different little kind of HTML website just to grab that data and then download it as a CSV file. And then we use Edge Impulse to split. We did 1 minute of recordings, and then Edge Impulse automatically splits that into 1 second samples for each strike.
So this is the initial results. So this is the raw data we get from the IMU. So we can see there's 6 features. XYE in accelerometer and XYZ in gyroscope. And this first one is an example of, I think, a horizontal strike, and this is an example of a vertical strike. And this is what they look like in time domain. And from time domain, we do a spectral feature, and we turn them into a frequency domain, which is the next level. Ta-da! So time to frequency. And after we convert all the raw data into frequency domain, next slide, we can see that they will group very neatly into distinct clusters. And this is what we use to train our model. And this is 100 samples per category. So we have vertical strike, horizontal strike, and an idle state for returning to like a neutral position. And yeah.
So our machine learning model takes basically 126 input features that are extracted from the IMU, and basically Edge Impulse created these features automatically using the generate features thing. And basically we have the 126 input features connected to 2 fully connected layers. The first one having 20 neurons and then 10 neurons. And these all use ReLU activation, which introduces a non-linearity. And then we have the final output layer being softmax across 4, or it's supposed to be 3 neurons. So we have horizontal, vertical, and idle probabilities. And then out of that, the highest probability determines the predicted strike classification, basically. And this is basically just like a visualization of what I just said. So the 126 input features, 2 fully connected layers with ReLU activation, and then that should be 4 output neurons. Or sorry, 3 output neurons. It's 4, but it's not updated correctly. But yeah, softmax output.
And so these are the 2 required advanced components we've included in our project because it's a group of 3. So we need to include 2 advanced components. So one is we can't collect all our data. We didn't use publicly available data set. We did our own data collection. And the other one is we deployed web interfaces to interact with the onboard machine learning, and it can be accessed through an HTML script. We will show in a few slides. This is our model after training. So accuracy is pretty good, and this is because our data is pretty clean. Now, interactive session. There's 3 possible model size. Which one do you think? People who think is 16.8 kb, raise their hands. 1, 2, 3. Who thinks it's 78? 2, 3. 184? Okay, no one. And the correct answer is 16! It's a very, very small model. Yeah,
Thanks to the magic of quantization.
exactly. Indeed. Live demo time.
Alright, so I'm going to change this to move over to show our web server. So we have our Arduino here at the tip, and then it's connected to my phone for power. And then it's connecting over Bluetooth to my laptop. So we're going to connect it. And then it's basically just going to get output from the Arduino over Bluetooth. So it's kind of visualizing. And then it basically does 1 second of sampling, outputs the predicted output, and then samples after 2 more seconds, and etc.
So when holding it still, it's predicting it to be in the idle state. And at the next sample, when I do a strike, it should do vertical. Yay! Horizontal. Horizontal. Vertical.
Sometimes the vertical misclassifies as horizontal.
Yeah, so you can see it's working. It's not perfect. There's future works that can be done, but this is a proof of concept that a very, very small model, 16 KB, can be deployed, inference at edge. There's no computation happening on the web. Everything's up here, and it can talk to the outside world through a web interface. Here are some of the key challenges we ran into during our development. The first one is it's really time consuming to collect 100 samples by hand. So what we did is we wrote a little logger on HTML, and we just continually sample for like a minute, about a minute, and then we get this really long continuous time domain data into edge impulse, and then use a split function in data collection to split it into like 1 second sliding window around each strike. So that saves a lot of time. Another thing is, how can we categorize the state between strikes? So what we did was we only read the 1 second when it's reading sampling at the interface, web interface, inference web interface, and then that 1 second of data is then processed into a categorization and then outputted to the output terminal. So next steps, more accuracy. Some strikes, for example, diagonal strikes, it was being confused as horizontal within our internal testing, which is why we decided to drop it for the final presentation. That can be better categorized if we have rasterized the IMU data into a 3D cube and applied some visual CNN convolution units to better distinguish similar strikes between like a diagonal strike and horizontal strikes. So that's some next steps we could do if we have more time.
So yeah, basically overall, we think the strike classifier was reasonably successful in classifying the sword strikes, considering that we had to broadcast the results over Bluetooth in real time and then process it with the web. Basically, this integration makes it very easy to classify sword strikes because, especially due to the Bluetooth integration, you just put a lightweight Arduino, don't need that much size on it. The main issue is you have to externally power it, which is why we have this big phone connected to it. But if you find a way to power it easily, you can easily attach this to a sword, and then, for example, in like a real-life fencing match, you can classify the sword strikes in real time into a device somewhere else in the room. and then you can make like a transcript of all the strikes used, or really use it in whatever way you want. Or you could create some sort of training program of like try to become a better fencer, saying, oh, your strike was too slow here, things like that.
That's our project.
And yeah, that's everything. Thank you.